Hi, in this OSLO video, we're going to show you how to use the command line as a calculator. You can use this as a general calculator, or you can use it to do things in the program, which I have found to be an incredible quality of life improvement to use this type of feature. I use it all the time, this kind of stuff. First thing that you should know in order to use this most effectively is some idea of what the math functions are available. So if you go into the help, there's actually a math library, and if you have trouble finding it, just type in math library or just type in math, and you can start finding these sorts of things. But where this is in the program is under programming and programming libraries. There's the math library, and right here I've just clicked on the standard math and trig functions, and you can see we have things like arc, cosine, sine, ceilings, logs, the typical kinds of things that you'd find in a scientific calculator. And with C syntax is how this is actually being used. So in the example I'm going to show, we're going to use arcsine. And the other thing I'm going to show is using this dr global variable. Dr converts from degrees to radians, so sine of 45 times dr puts the argument in radians, and that's what the sine function wants. In our case, we're going to do an arcsine in the example I'm going to show, and so I'm just going to divide by that dr, and that is taking care of that pi divided by 180 or 180 over pi factor that you get depending on which way you are converting. So that's what we're going to use in my ultimate little example. But I'm going to show you something simpler first. Certainly things like multiply and subtract and things like that, you can just type into the command line 2 plus 3, that's 5. Oops, I actually accidentally changed that. So I can X out of this, come back in. If I don't want it to actually change something, what I usually do is just go to some sort of field where I know it's not going to change. That's one thing you have to be careful about when you do this. But if I do 2 star to the 4, that's 2 to the 4th power, so that should be 16, and there's my result of 16. It's certainly nice to use print or aprint to put the result into the text window, especially aprint if you want to be able to access the cell. So here I have a little example lens, and I've just cleared the spreadsheet buffer here. What we're going to do is we're actually going to do two things. The first thing is, let's say I want to scale this aperture radius by 1.25, so I can do just times 1.25. This is a huge use for this. So now it changed that. Sure, that's not that interesting in this particular case, but what if you had an unrounded number or something really messy, or you wanted to multiply by 2.45 or some number like that? In that case, normal you'd be sitting there with a calculator, you'd be doing the calculation and typing in numbers. It's so fast and so easy to do it this way. Such a huge beneficial thing. The rest of the video, I'm going to show an example where I've just got this chunk of glass here, and what I'm going to do, this is just a Hoya glass, I'm just going to take and put an angle onto here so that I match the condition of total internal reflection. So just a quick physics review, total internal reflection occurs when Snell's law is at a point where the angle coming out is exactly 90 degrees. And if you go any further beyond that, you actually get the light reflecting back into the inside of the material. This of course only works, and so here's the condition where we solve for theta 2 to be 90 degrees, so the theta 1 becomes the critical angle, and it's just this arcsine function. So and it's the index of 2 divided by the index of 1. Now one key thing is the index 1, in other words the index that you're coming out of, needs to be higher than the index of 2, or you can't get the condition of total internal reflection. This of course is a guiding principle for things like waveguides, light pipes, and of course things like prisms is where this is used a lot in optics. So let's go ahead and solve to see if we can get this condition, and we're going to use this as a calculator here. So the first thing I need, of course, is what are the indices of refraction. So I click here on the refractive index data, and now right here inside of the spreadsheet I've got a number that's available. Now I could go into here right now and go into the coordinate and just type in the formula and get the number to dump in directly, but I'm going to show you instead printing it out into the text window here and then using that to as the coordinates. So let's just go ahead and do this. So we've got our indices, and our formula is that we need the arcsine of 1, which is the second index that we're going into, we're going back into air, divided by this refractive index. That's cell number A3. You can also use the SSB command if you want, but when I use the calculator, it's just as easy to do this. And now I need to divide that by dr, and that'll get me a number in degrees. However, if I did that, it would just show up here in this little field. That's actually not that useful. So I'm going to use the aprint command because that'll create a new spreadsheet buffer entry for this number. So here's the number 39.130847 or whatever it is. You can see the full number here with the spreadsheet buffer. So that's cell A5. So now I just need to go into here. Oops, actually need to pick the correct one. I need to pick the second surface. I go to coordinates, and TLA rotates about the x-axis. The x-axis is the one perpendicular to the screen here, so that's the one I want. And then again, that's A5. So I just go and I type in A5. There's my number. I go here, and now it's total internally reflecting. You can see it's total internally reflecting because the light is no longer going through. By the way, this is something to be very careful about when you do designs, is if you see lenses, if you see rays being truncated like this, it's likely total internal reflection is the culprit when you go from a higher index to a lower index material, something that people that do a lot of optical engineering and design pay a lot of attention to. Now, one thing I can do here just to sort of show, if we come here and let's just make it 39 instead, I would expect then the light's going to be coming out nearly at 90 degrees for that entire beam. And that is indeed what happens. So I hope you enjoyed this video showing the flexibility of OSLO's command line, being able to use it for calculations, and a huge quality of life type of thing when you're trying to edit things in the program. Saves you a lot of typing of numbers, and it's really easy to use.